Yes, noon, yeah. But if I finish a few minutes early because I'm hungry, it's also. So, yeah. So, where were we? We were. So right now we're looking at second question, which is interference channel, another building block, and we were trying to ask whether it's optimal or suboptimal. Let me remind you what the setting is. So you have two point-to-point communications, and there is some crosstalk, and you're really asking whether this particular region, which is a massive, ugly region, whether this is, I don't want to call it ugly, but it is really, it's hard to compute this. Okay. Now, even if you want to numerically compute this for generic binary input, binary output channels, I don't know. It's beyond, the dimensionality is too large to compute this region. So you are asking whether this is optimal or not. So first step is to find a class where this region simplifies and is yet not too trivial. Because for trivial things, yes, this captures a lot of intuition, so you cannot be too trivial. And so after a few years of work, we ended up with this channel, which is simple enough. And so the setting the setting is the following. So in this setting, there's no noise at second receiver. Second receiver hears exactly what the second sender sent without any noise. And there's only interference at the first receiver. So that's what I call a clean. Clean shows the second is clean, and the Z interference. Now in this particular setting, the 7 inequalities in the previous setting, the region is exactly the same as this region. It's not hard to show that the region is given by these two expressions, and the 7 is exactly the same. And let's just denote this region. There's only one channel here, so I'm going to denote this region R of WA. So to test the optimality of Han Kobayashi, is enough to see whether this region is optimal for this particular class channel. So as I said before, I always want to test the optimality by testing the hyperplane, whether it doubles. It turns out that when lambda is between 0 and 1, you can compute the S lambda, the weighted sum rate is given by this particular expression, then U2 disappears, and you get essentially this form. And it turns out that this is subadditive. So you have that this expression is subadditive, and this implies the optimality of the weighted sum rate in this particular region. So we started off trying to prove suboptimality, and in this region we proved optimality. And this is, this is again a case of things, if it's too trivial, it's optimal, right? So, but now what about lambda bigger than 1? For lambda bigger than 1, you have the following expression. You have to now take, go back here, you have to take this expression and this expression. So it's a different pair you have to take, and you get the following expression. So it becomes a maximum over P of x1, x2 for some leading term plus the upper concave envelope. And here it's not easy to say what the upper concave envelope is. In the previous case it was easy, so in this case it's not easy. But when x2 is binary, the upper concave envelope essentially, so probability distribution over binary variable, single variable thing. So it's a single variable concave envelope. And what we can show is that this has at most 2 inflection points. Okay, so in general we'll have a picture like this. So the upper concave envelope will be a picture in general like this. So now you can try to find hyperplane where it is tangentially. At least you can numerically compute this to hide this shape. And now you can ask for the same question: can we numerically test whether these two are equal for channels? Now it's feasible at least to do a computer. And the moment we do this, we get a whole bunch of counter examples. So this is a particular lambda. This is a channel for which we get counter examples. Okay, so this is the case. So if you can make the right guess to test the optimality, then you can clearly answer the optimality. So the whole difficulty is here is coming up with the right channel, which is difficult enough but easy enough to. Now the only thing that a person might ask, okay, it's rather close. Is this a numerical error or is it? Oh no, so lambda is, let me tell you what lambda is. So lambda is, so in general you have, some region like this. Right? Lambda R1 plus R2. When lambda is 0, you are maximizing this point. You are getting this. Right? When lambda is 1, you are maximizing some rate, which is. No, it has nothing to do with which code book you choose. It is just this, yeah, it is just some slope of the region. And so it turns out that in this case, it turns out that you have a flat region and you get some optimality and you get some. No particular coding. It's just a convex problem. So the only problem is, so one thing you might ask is, okay, this is a numerical problem. Is it like, how confident are we that this is really a subadditivity proof, right? Because you have to be, because an important setting, different channel, you have to be reasonably confident that this is not a question of. So that's this. So you can see that these are all now computer generated. This is nice. So it cannot have been randomly generated by a computer. So this is something we looked at. So here's a particular channel. So we look at lambda equal to 2. What happens here? When x2 is 0, when second person transmits 0, y1 gets only 0. Irrespective of what x1 transmits, he only gets a 0. When x2 is 1, this is like a channel where 0 flips by probability half and 1 is kept constant. And here we want to compute the maximum of the lambda sum rate. So I want to compute maximum over all x1, x2. So this is just two variables of this particular expression. It turns out this is again a single variable thing. So if I denote this by fpq, where p is probability of x1 equals 0 and probability of x2 equals 0, then the thing I want to compute the concave envelope over is the following expression, where hb of x is minus x log x minus 1 minus x log 1 minus. That's the binary entropy function. And then you want to see what is the upper concave of this with respect to q. So it turns out that you can explicitly compute the upper concave envelope. So it's either fpq when q is bigger than 1 minus p, or it's given by a line segment which connects 2 points. So the picture is exactly like this. So the upper concave envelope here is you either join the line segment, and here the things are so nice that we can explicitly compute this. So there's no numerical error. So now I just want to compute. So how do I compute the how do I compute the Hahn-Kobayashi region? One letter, I just had to compute the maximum of 2 R1 plus R2 is given by the maximum over TPQ for PQ in 0, 1 cross 0, 1, which is where this is exactly the variable. Okay, so at least now we've removed the numerical inaccuracy of computing the upper concave envelope. So that's explicit. There's no. So now you can plot this. If I plot this, you see somewhere the maximum is here, and if I do numerically, you get something like this. Okay, this should be enough for most people. But if you want to be even more formal and you want to say that there is a gap, you can do interval arithmetic. So this is a very nice scheme where if you have functions which are logarithms and analytic functions, then what it does is it just grids the space and bounds it in everything. You just upper lower bound the functions explicitly, and if you do it, you can show that maximum will lie between these two values. In fact, this is very close to true maximum. The lower bound is very close to true maximum because you can actually compute it. Upper bound is always the thing that you want to bound it. And now when you do the two-letter, you can easily get something beyond this bound. Okay, so this is not a numerical. And in fact, in two-letter, you see that the optimized distribution is the repetition coding. It's very, very different. So across time, you are completely correlated. It's very, very far from independent coding. You're doing something very, very, very different. Okay, so that is basically the Hahn-Kobayashi counterexample. So now you may ask, okay, so we did this for Hahn-Kobayashi. The other big question was Martin for broadcast. Why can't we do the same thing for Martin? In fact, that's what I started with. I started with Martin, studying Martin, and then I got stuck and I came back to this. Came to this. So let's see what I know about Martin for some time. So for Martin, if you peel and look at this, what you want to ask is whether the following function is subadditive. So you take an alpha in 0, 1, and for every x you take maximum PUV given x of lambda IUY plus IVZ minus IUV. And you take the upper count, now it's a function of P of x because channel is fixed and there's no auxiliaries anymore. I removed the auxiliaries by taking the maximization. You take the upper concave envelope of this with respect to distribution on x. I'm asking whether this is subadditive. If it is subadditive, then Martin is optimal. And if it's not, if it's superadditive, then you should be able to get a channel where there's a counter example. So really the optimality of Martin is just testing the stability of this. Okay. So Venkat, Anantaram and Amin, and we have conjectured this stability because we did a lot of tests and we could not find a counter example. But we also get something very, very nice. We can prove stability when alpha is at the two extreme points. So we do have some math proof. And we also, there's something very, very nice happening here. We can also show that to compute this functional, it's enough to look at u and v, so that the size of u and size of v is at most x plus 1. Okay. And now, once you have this, at least for certain things, we can do explicit numerical. We don't get counter example. So now, why is, and this is something which is very striking to me. There are two reasons why. So u is kind of the message that you transmit to one receiver. V is the message you transmit to the other receiver. So this is saying that there is inherent trade-off in the sizes of u and v. It's exactly the same as the broadcast channel trade-off. Operationally, it's very, very pleasing. Second, this theorem is not true if I just want to compute the maximum of this function. It's not true that to compute the maximum of this function, I just need to make this restriction. That's not true. In fact, it's false. But what happens what our proof shows that in general you have upper concave envelope. At all these points, this is enough. And at these points, you have something weird happen. Okay, that's what, and this comes from dual representative, we'll come to later. So there is something, even though Martin came up with the scheme arbitrarily, when you look at the optimizers, it is showing that it is somehow intrinsically related to the setting. Okay, there are some, so if I could, so one thing is I don't have a good geometric understanding of the optimizers here. I don't have an equivalent concave envelope kind of understanding here. Because this is not doing a concave envelope, it's doing something else. And I really don't have an understanding of what these auxiliaries are doing. If I could have a geometric intuition, that would be a good first step. Okay, so that's the, so here so my belief is that this is optimal. And there are various reasons why, but if it's hard, you can so this could be numerically tested, right? So many people can just run it and see whether it's optimal or not. If it's not optimal, then you can get a counterexample, you're done, right? But if it's optimal over like many people's tests over many things, then there might be a reason why it's optimal. Right? That's kind of it. Okay, that's so to demonstrate super additivity, we need to identify a sufficiently simple class where evaluation of region is possible. But it's a non-convex optimization and super additivity. So we also use the same idea to show that supervision coding is suboptimal. This is also a very nice setting. This also gives intuition on how to improve these schemes when you have 3 receivers and more. Okay, I'm not going to talk about it, but the idea has been used elsewhere. Okay, so this is the second. It's a fast overview of what interference channel. Now I want to spend some time on the last part, okay, which is I want to go slowly because I want to lift it up to. Yes. Yes. The difficulty, okay, there are two things, right? If there are enough people who do this numerical test, and if somebody can come up with a counterexample, you're done, right? And that's easy. So you just need a supercomputer to run for some time or something else to run for some time, which will test. But if people cannot find a counterexample easily, that may be indicative that this stability holds. Then you need a math proof. Yes. Yes. So one way to give, we did yeah. Yes. Yes. So in interference channel, the moment I could get my hand on some even binary instances, I could find counterexamples. Here I can do any binary instance. I can even do binary cross ternary. No counterexamples. Okay. So here I can evaluate much more than for interference channel. Only, okay, binary and binary cross ternary. That means I can take x1 to binary, x2 to ternary. No. It may give a gap to capacity. It may give you a. you need, okay, either you had to, if it's a multiplicative gap, it'll blow up. Yes, but if it's an additive gap, you need the additive errors to add up to a constant, right? So you need some kind of. Okay, so this is. Okay. So now let me come back and we will, this is going to tie up to some of Varun's talk yesterday. How does it, I mean, what is the family of non-convex problems? How is it related to problems of interest in other fields? And then I will put some unifying observations and conjectures which will tie up the things. Which is meant to say that not, this may be of interest to people outside information theory, this particular field, because you have something nice. Okay. So what we're doing is not non-convex particularly as much as we want to test subadditivity of expressions of this form, okay, or some linear combinations of entropies of subsets, okay. Even Varun's case where you have linear, I mean, he was looking at linear transformations, so all you need to put is measure which is mass only on the linear, you just put a measure which is not absolutely continuous with a Lebesgue measure, right? You just put those mass and you will get this form. So this is a very general form. This captures all what we saw yesterday and today. We want to test subadditivity of this, and so now I'm going to say how can we test subadditivity of this. So you look at the Fenchel dual, Fenkel dual. So you take a hyperplane gamma 1, you define the function g1 of gamma 1 is the maximum or all mu of x of this form. You define g2 of gamma 2. So you take another form, and you take g12 of gamma 1 gamma 2. So this subadditivity of the concave envelope is exactly same as asking, is this equality true? Or in particular, it's asking, is the maximizer of this functional a product distribution? Yes, so the Fenchel dual of the upper concave, okay, you take a function, you take the Fenchel dual, you take the dual of the Fenchel dual will give the upper concave envelope. Okay, so that's why these two. So now you see why non-concave comes. So all you want to show is not find the optimizer. You want to ask whether the optimizer is a product form. Okay, so basically at the end of this, testing subadditivity of this is same as asking whether this non-convex problem has a product maximizer. And this dual form was exactly used in getting this bound u plus v less than or equal to x plus 1 by Venkat and Amin and myself. Because this is how you can, using this we can just get the points which are really in the dual form. Okay, this is used. So now you can ask, are there other fields? You saw some of it yesterday. It says are there other fields where the same family shows up? Okay? And here I'm going to show a very small family, but you can see the other thing. So let's look at hypercontractility. This is something that's studied in other fields. So we say a distribution xy is PQ hypercontractive if for any function g of y, so Markov operator which maps it to, which operates on g, the p norm of the Markov operator, where p is a higher norm, is less than the qth norm for any g. So this is why it's so conditional expression is a contraction. So it's clear that if I put p equal to q, this is true. That's just a contraction of the Markov operator. But now I want hypercontraction, so I want to replace it by a higher norm. Okay, where Zp is the norm. And this is studied in. It was not studied in. It is mainly studied in functional analysis. It came from physics. Then now CS theory, people use it and so on. So what I've showed a few years ago is that it's along the lines of Carlin Cordero kind of evaluation, but it's for a limited setting. I showed that this is exactly same as asking if I look at this linear functional entropies. So you can think of this as a functional joint distribution, and if I take the upper concave envelope of this functional, does it match the function value at the mu xy? So then if it matches, then mu is PQ hypercontractive. So for every P and Q, I can draw this functional that changes with P and Q, and I'm asking what are the distributions at which the function and the upper concave match? Those are exactly the distributions at which they are PQ hypercontractive. That's an if and only if characterization. And now you see the linear forms of entropies coming up. Okay, so that, and the concave envelope. What's the expectation of G of Y given X? But usually it's put in this language, and they have this some Markov chains and semi-group operator. This is the way some people write it, but you can also write it as BFG. Okay, so why is hypercontractility interesting to many people? Because it satisfies the property called tensorization. This is the language I use. So if what is tensorization? It means that if x1, y1 is PQ hypercontractive, x2, y2 is PQ hypercontractive, and they're independent, then the pair x1, x2 to the pair y1, y2 is also PQ hypercontractive. And this helps you get around the curse dimensionality. It's like, I mean, you have this kind of very nice property, and that's why it's useful. Now, it's rather immediate that tensorization is exactly same as subadditivity. Okay, so tensorization hypercontractility is exactly same as subadditivity. It's just like a 3-line proof or 4-line proof. It's not hard to see. I mean, it's a good exercise because it's a good exercise to think for yourself why it's true. Okay. Yes, so they normally look at it in terms of Markov chains over time and how much it contracts. It actually usually, at least in infinite theory, is like how much it spreads. You can control how much the probability spreads. If you start from some point, you want to say how much it spreads and where is the mass located at few points. I mean, like after like 10 steps, like where will the mass be? How large will be the set of points where the mass is concentrated and so on. No, like you mean P and Q. So if P equal to Q, it's trivially true. So you're really interested in like P much larger than Q, but then it may not be hypercontractive, right? So you need to figure out which for every Markov chain, which is the right P and Q, and that's a hard question. That's a non-convex problem. I'll come to that in a minute. So yes. Oh, then okay. So it normally says that it's almost saying that independence. It's almost saying independence. Like it's so one limit is independent, one is IID. So when P is much larger, if P is insane, then you say that the next step is independent of the previous step. So it's like a fast mixing chain. So and if P is if P and Q very close, then it's like a slow mixing, and so it doesn't spread very much. So I claim that this is also Carl and Cordero. I claim it is kind of serendipitous because we were not looking for it. And it's rediscovery. I call it rediscovery because the first link between hypercontractility and information measures was by Alsferi and Gach in '76. Completely forgotten in infinite theory community and probability community because Kerner Martin did a different way, and that is what infinite theory community. And then we kind of rediscovered this, and that's spurring a lot of work. Okay. So now coming back to saying computation of the PQ, optimal PQ, is considered hard. So the only thing that is only things were known in some sense, it was known when X is uniform and binary symmetric. That's a noise operator in the Fourier analysis literature of TCS. So the Bonami-Wegner inequality, you know the best P and Q, and this was done in the forward direction by Bonami-Wegner, and there's something called reverse hypercontractility by Christoph Borel in '82, and Gross also did this for jointly Gaussian things. Yes. So you want to compute the region. You want to compute the hypercontractive region. And that's considered for a given xy. So for every xy, you have this another problem. You want to find the PQ, and that's hard. So let me ask, so what we came up from a different angle, we said, okay, we want to compute things. Okay, if there are information theorists, wait, I want to tell one more thing. Computing hypercontractivity is exactly same as computing the region or what is known as the gray Wiener source coding problem. So there is an exact equivalence to information theory. So optimality of schemes. So we came differently from evaluating optimality of things. So you can ask, does our intuition help you compute more hypercontract parameters? So yes, we could, and we could do it for, say, rate channel. And this question was asked to me by somebody from TIFR, Jayakumar. Jayakumar was visiting me in Bombay when he asked me, he and Venkat Guruswamy asked me whether I can compute this because they want to use it for some distributional complexity. And this, so there are two papers, one is the forward direction, one is the reverse direction. The reverse direction is more interesting because it has some nice features. So there's something called reverse hypercontractivity, there's reverse Braskamp-Leib, there's reverse reverse EPI, all of this is known. So that's what we can. So basically the ideas we use is you essentially find a lower dimensional manifold that contains all stationary points, analyze it on this manifold because it's much smaller dimension, and then use properties of the points to get suboptimality. That's kind of the rough idea of what happens. Okay, so we won't test the optimality of coding schemes in independent theory. We saw some, but many remain open. And we want to compute the optimizers of several non-convex functions. We developed some tools. There's still one part left, so don't. We developed some new tools with techniques of Gaussian optimality of subadditivity, optimal auxiliaries correspond to computational concave envelopes. There's the min-max which we use, but more ideas and tools definitely seem necessary. And these specific families of non-convex functions also appear in other fields. The tools can be used to get some new results. But what I want to do is put it all together to put some unifying observations and some conjectures, which I think, these are still preliminary, but I think if you can refine, they may not be in the perfectly refined form, but I think it's very useful. Okay. So these are the meta theorems or meta things. So we're looking at this family of linear combinatorial entropies, and we weren't interested in testing subadditivity of mu x alpha s x. So I claim that this has a global tensorization property if the same thing, if a product distribution maximizes this function. That's what I said before. Subadditivity is same as